Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Eric Sandquist with us today. Hey, Eric.
Hello.
How is it going on this January 26th? Do you have lots of snow on the ground?
Zero. I don't think we've had snow on the ground in the last, well, at least not here for many, many years.
So where are you at? What's your geolocation?
In San Diego.
San Diego. Yeah, we don't get a lot of snow there in San Diego.
The nice thing is that we can drive up to the mountains in 45 minutes and get to snow if we want to, but we don't have to.
Yeah, East San Diego has some good sized hills, indeed. Not a lot of snow in Phoenix either on this January 26th, but we are definitely in our winter mode. So we did get down to a little bit below freezing last night, so a little chilly, but all good. That's a pretty awesome, was that a bike tire or a tube on your left there? What is that?
Yeah, I blew out a tire.
Oh no.
Days ago.
So now it's waiting for repair.
Yeah.
Very cool. Very good. All righty. And Eric, what do you like to do for research?
I definitely call myself a stellar astrophysicist.
Cool.
Used to be more theoretical, but doing a lot of observations these days and trying to learn about how the stars work. Not the older dying stars like I guess you work on, but the ones that are still kicking.
Oh, I like the ones that are still kicking. In some sense, they're the most fun. Very cool. So you're the proverbial double threat. He's got a little theory, got a little observation going. Awesome. Now all you have to do is add instrumentation, and you'll be the proverbial triple threat. So
I think that's going to be a no.
All right, very good. And that is going to bring us to this very awesome AJ article. It's open access. You can go get it for free, people. Go ahead and get a read. And evolved eclipsing binaries in the age of the open cluster NGC 752. And Eric, take us away.
So, yeah, so I mean, just the sort of general theme of this is that in astronomy in general, when we're talking about stars, we don't very often have good information about the masses of the stars, and that's such an incredibly important piece of information to not have.
Right.
Determines, as you know, it determines just about everything about the star's characteristics and how it's going to live its life, how it's going to die. So, and a recent theme in my life is that I've been doing mass measurements for stars that are just starting to leave the main sequence.
Cool.
Not sort of the stars that are in the middle of their lives doing mostly nothing interesting. I mean, they're just sort of sitting there doing the same thing for
a while,
billions of years. But I'm looking for ones where we can measure the masses of stars that have evolved off the main sequence or started to evolve off the main sequence.
Okay.
And the main reason for that is that then the characteristics of the stars change very rapidly. You can measure interesting changes, and you can get very precise ages for the stars as a result of that.
Cool.
So, binary stars make the perfect laboratory for that. So you can make, we think we understand the physics of binary star orbits very well. There's no real argument about, Kepler's laws and Newton's gravity work perfectly fine in describing the orbits. So we can use that simplicity to our advantage and get really precise masses for binary stars where we can characterize the orbits of the stars.
Cool. Okay.
So what we do is we look for these binary stars in star clusters, and then because we try and apply the age that we get from one or two stars in the cluster to the cluster as a whole.
Okay.
And get a broader range of information about how the stars are working.
Okay.
So in this particular paper, we're talking about NGC 752, which maybe is not a particularly interesting name, but it's a very nearby cluster.
That helps.
And it's a relatively old cluster as clusters go. They start to tend to break up in our galaxy
Yeah.
in the several 100 million year to a billion year range.
Mm-hmm.
So this one is something like 1.5 billion years old.
Okay.
But it's the closeness of it is also relatively nice because there's a whole lot of information available on stars in this cluster. And that will show up in various places in this paper.
Nice. Nice.
So
Okay.
maybe one of the things to point out about NGC 752 is that this age also makes it kind of interesting. The stars that are leaving the main sequence right now are pretty much right at a transition point between more massive stars and less massive stars. They are stars that are starting to produce degenerate cores in the centers of the star when they're evolving onto the giant branch.
Mm-hmm.
They have what's called a helium flash when they ignite helium after they leave the main sequence.
Mm-hmm.
Just a little bit younger star clusters, the stars when they leave the main sequence and when they ignite helium, they don't do it in a degenerate core like a proto white dwarf.
Right.
The star's core is an ideal gas. So the stars behave in a different way once they leave the main sequence and they ignite helium.
Uh-huh.
This particular cluster is showing us stars of both flavors, ones that ignite helium degenerately and ones that don't.
Cool. So we can kind of get that mass where that transition occurs.
Yeah, so I mean, I think that's one of the interesting aspects of this particular paper. That will be a consequence of all this.
Cool.
So just as some other background, the stars in NGC 752 are kind of about the same metallicity as the sun, maybe slightly more metal poor.
Okay.
And that also has some effects on the analysis. But what we did, we looked around for eclipsing binaries in this cluster. And the one that's been known for a long time is called DS Andromeda. It's a relatively bright one. It's also kind of a weirdo, we find out. There's two stars that are orbiting around each other almost exactly once a day.
Okay.
Which makes it fun to try and observe when your planet is rotating once a day.
Right, it's moving. Very good. Nice.
So, I mean, one of the consequences also is that these two stars, they are seemingly detached from each other. So for the most part, they look at the simplest level like they are evolving separately from each other.
Cool.
But there are strong tidal interactions between the stars, relatively strong ones anyway.
Okay.
One of the stars gets a little bit distorted.
Okay.
It didn't seem like it was too bad. That it seemed like we could probably do something along the lines of these age determinations. So that's why we've been working on this potentially for, well, not potentially, for a long time, for something like 10 years.
There you
go. Towards the end of the project, we actually found out that there was another one that was analyzable. It's actually a little bit brighter, and it's a wider binary where it's clearer that the two stars are not interacting with each other. And even though they are relatively close, they are far enough apart that they don't seem to be strongly gravitationally interacting.
It's BD 37410.
Correct. So I'm probably not going to repeat that many times because
it's a mouthful.
Yeah. So what we do, one of the main things that we need to do is to measure how fast the two stars are moving around, characterize the orbits of the stars in that way. That's mainly what leads to the mass. We do have to for people who've taken astronomy classes, we do need to know about the inclination of the orbit. Both of these binaries are eclipsing, so we know that the orbit is pretty close to edge on. Which allows us to tell that the radial velocities are a direct indication of how fast the stars are actually moving around their orbits.
Right.
That's what we leverage for the masses.
Cool. I'm with you.
All right, so I think we can skip down a little bit here.
Okay. Reddening and distance, membership.
I guess we can go to like figure 2, maybe.
Figure 2. Let's go to figure 2. Figure 2. Ah, there we go. Beautiful. Okay.
So it's one example of
DS. Okay.
Some data that has been available out there in the internet that we could apply to this project. It's one of the indications that this particular binary system is eclipsing.
Indeed.
It's not quite as obvious in this particular figure as it is in figure 3, which maybe is a good one to go to.
Okay, let's go to figure 3. Lots more data there.
But so this is again some publicly accessible data that we applied to the project, but this maybe indicates more clearly that this is a totally eclipsing binary star, which is kind of the holy grail for people who do binary stars. It can give you very precise size measurements for stars.
Right. Cool.
And it turns out that that's particularly important for the kinds of things that I'm doing, because when a star starts to leave the main sequence, the radius of the star is one of the characteristics that changes very rapidly as the star moves off the main sequence and starts to evolve. So if you can measure the radius of the star very precisely, and you know the mass also is at the same time, that gives you precision on age.
Yes.
A combination of those two things.
Yes.
Knowing one by itself is not going to help all that much, but the combination is very important.
Cool. Nice. Very nice.
So if you want to see some of the other gory details, we can quickly go down to figure 12.
Sure. Let's go down to figure 12. Let's take a look at that. Where am I at here? 23, a little too far. And 13, 12. There we go. Oh, yes.
We have a lot of data on this star. So these are all different filter bands from the ultraviolet far into the infrared. So the combination of all this data, fitting all this data, gives us those very precise sizes for the two stars. It also gives us good indications of what the temperatures of the two stars are. If you look very, very carefully at these light curves, you start to see that there are differences in the depths of the eclipses.
Yes.
Over in the infrared on the right-hand side, you have eclipses that are closer in size to each other, but over on the blue-hand side, the left-hand side, you have primary star eclipses. The deeper eclipses are quite a bit deeper than the secondary eclipses.
No, indeed.
Cool ones.
Yeah. Very cool. Okay.
So
you got tests on here as well? So you got test data on here?
Yeah, pretty much got our hands on every bit of data that we could.
All of it. Okay, good. All right. Very nice.
And that's just another one of these themes that there's, because this is such a close cluster, there's so much data available that could be used and can give us that precision and very clearly measuring the characteristics of these stars.
Okay.
So maybe we could jump down to figure 13 just for a quick look at some of the other data that we had to get for this binary star. This is the radial velocity measurements in particular.
Okay.
The top is showing us how fast the stars are orbiting around, and that's what leads us to the masses. We have to do our best in very precisely measuring the velocities of the stars, in spite of the fact that they are rotating very fast. they're in a very tight binary. They're tidally locked to each other.
Okay. Okay.
So one of the stars is rotating like I think it was 100 and some kilometers a second, and the other one's 50 kilometers a second,
Huh?
which makes it a little bit challenging to measure the velocities from the spectra, but
Mm-hmm.
I think we did a good job. And I do want to shout out to Matt Chatron, one of my collaborators who took a lot of the blue points in this data, and also a former graduate student, colleague of mine.
Mm-hmm.
Oh, and while we're here, I mentioned Andrew Buckner, who's an undergraduate who's worked with me on this project for maybe longer than he should have.
We're here now. We got there. So very good.
He helped a lot with the photometry on that particular system.
Nice. Okay. Good shout out. Okay. And where we were down around 12 or 13, where would you like to go next?
Let's see, we can probably pop back. Well, just to quickly show you some information, you can go down to 14 and 15, maybe.
Sure. Let's do 14. There we go. Test-based photometry. There we go.
So this is the other binary star that we worked on.
BD.
It has its own quirks. We only have test data on this particular one.
Yeah.
It's a longer period binary, so it's understandably harder to get lots of data on the eclipses, but the precision of test data is so nice that we can use this alone and get very nice constraints on the sizes of the stars. This particular binary is a little bit interesting, I guess, from an eclipsing binary point of view, in that it only has one eclipse per orbit.
Okay.
And if you think about that a little bit, that's a little bit weird. If you had circular orbits, you should have eclipses, 2 eclipses every cycle, but this one does not. It's actually a little bit eccentric.
Right. Okay.
So it turns out that this one is eclipsing close to Periastron, its closest approach. The other near approach on the sky does not eclipse, so it's maybe not the traditional binary star astronomer might not want to pay attention to this, but it turns out if the eclipse, even if it does have only one eclipse, if the orbit is wide enough, you still get a good leverage on the inclination.
Okay.
If you want to think about it this way, there's a very clear limit to the inclination of the orbit. It definitely has one eclipse per orbit. So it turns out if you have a wide orbit, the inclination is pretty strongly limited by the angles where you would get 2 and where you would get 0.
Yeah.
So in spite of the fact that this has just one eclipse, you can still get a very good inclination, and as a result, a very good mass for the 2 stars.
Okay.
Cluster. And that's, again, where figure 15 comes in, measuring radial velocities.
Very good. Let's see what we got here.
So it turns out there was a lot of radial velocity measurements for this star in the literature already. But again, another shout out to the collaborators, especially Katie Pilachowski and Sam Barden and Bob Matthew and Diane Harmer. They had radial velocities on this system, very, very precise radial velocities on this system that made this especially great to analyze. All those dark blue points just really filled out the radial velocity curve and allowed us to get very precise masses. They were actually looking for planets. I didn't know that their data was that they had this much data before I contacted them, but it was a happy coincidence, and
absolutely,
we, I think, all benefited from it.
Very good.
So, I mean, that's maybe for the binary star aficionados. I'm just trying to prove to you that we can get masses and radii for these stars very precisely. So where do we go from here? What we want is to get to ages.
Yes.
So if we go maybe back to figure 1.
Figure 1. Let's do figure 1. Brr, bang. Okay, we got some CMDs. Okay.
The light blue point and the light red point are the ones that, those are the combined brightness information for the 2 binary stars.
Okay.
The interesting thing to get about this is that they're both towards the end of that string of red points, small red points. Those are the stars that are leaving the main sequence.
Yes.
Very soon will become giants.
Mm-hmm.
And that's kind of the proof for a stellar astrophysicist that these are stars that are evolving. They're almost done with their core hydrogen burning.
Yep. Yep. Oh, yeah, it does. What are the okay. So you got some chemically peculiar ones in here too, I gather. Okay. Open circles. Okay.
Yep. So maybe getting down to the gritty here, if we take all that lovely photometry and velocity data and we fit them at masses and radii, and maybe we can pop down to figure 21.
Absolutely. Figure 21, 22, 21. Oh, we got some mass radius plots.
It's a kind of complicated figure, but this is kind of telling the story of these stars. If you imagine you have a star of a particular mass, it starts off as a main sequence star. It starts off at its smallest size.
Okay.
And as it evolves, it will get slowly bigger when it's on the main sequence. But then when it runs out of hydrogen at its core, its evolution accelerates, and its size, for one thing, accelerates upwards in size, overall size.
Okay.
So if you imagine, if you know the mass of one of these stars, and the 2 most massive stars that we've dealt with here are at around 1.7 times the mass of the sun.
Yes, right here.
Go upwards in this diagram, you're seeing these different colored curves are showing you where models predict the size of the star should be at different times. Going from 1.2 billion years with the violet curve up to 1.8 billion years with the black curve.
Okay.
So all those curves that are close together, those are basically showing you the main sequence part of the star's life. There aren't large changes in the size of the star for most of the time. But at least for the 1 or 2 of the panels, you see that there's this little dip and then this almost vertical line. Maybe the mist panel there.
Here, these? Yes. Okay.
So that's basically showing, the model showing us where the stars are running out of hydrogen and they're starting to move off the main sequence.
Right. You can see it here in the basket as well.
So that those curves really shoot up to dozens of times the size of the sun.
Yes.
The 2 that we measured, they have about 2 to 3 times the size of the sun, which is definitely showing us, according to the models, that the stars have been around for a while, and the changes that are resulting from the nuclear burning in the core of the star are leading to the star to slowly start to expand.
Okay. Structural changes. Yes. What is this more or less more horizontal black track for presumably 1.8? I mean, I see 1.8 here on parsec, and then this black one sort of jitters off across the curves, and you can kind of see that in all of them. What is that? Do you know what this black? Oh, it looks like it's a totally different model here.
So for in the star cluster game, one of the ways that we identify the age of a cluster is where the turnoff is, where the hottest stars on the main sequence are.
Yes.
That's not particularly obvious on these isochrones, the colored ones, the way they stand. So what I drew in was that weirdly shaped black line is where the turnoff was for all of those different
I
ages.
understand now. Got it. Thank you.
And that was important for this particular case because one of the binaries has a star that's essentially right at the turnoff.
Yep, right here and right there, depending on your model set, but right there. Okay.
So, I mean, if you go up to figure 20, maybe that kind of shows the same kind of thing. So,
oh, here we go.
Radius versus temperature of the star. So, as stars in a cluster age, the most massive main sequence stars will die over time, and the main sequence kind of peels back towards lower temperatures. That DS Andromeda A star, the more massive one, is essentially right at the turnoff. So, for a star cluster person, that's like, yay, we got one. Telling us exactly what the mass of the star is at the turnoff. And this is, the traditional way of finding the ages of clusters like this.
Yes.
But we have new information now. We have the mass of the star, and we can turn the screws more on the model makers, the stellar model makers, to see if they actually know what they're doing.
Oh,
Whether all the physics that they have in it is correct.
Okay, good. Tests are good. Yeah, I like that. Very good. I get it. I'm with you. Cool.
So it turns out from knowing that the star is at the turnoff of the cluster, it gives us a little bit of extra information, to test the models. Do the models predict that they get to the right mass, to the right radius at the right mass on the turnoff? And the models don't all agree on that particular fact. Those weirdly shaped black lines are not all at the same radius level.
Right.
So from a stellar astrophysics point of view, that does actually tell us something. And this seems to be directly related to some physics that's happening in the center of the star.
Okay.
These stars transport energy by convection in the center of the star.
Yes.
It turns out that's a very complicated process, and there are complications in actually putting that into the stellar models, as you well know. And we're not entirely sure how much of the center of the star is taken up with these convective, turbulent, complicated motions that carry the nuclear energy out of the center of the star, but as a consequence, they also mix up the fuel at the center of the star.
Yes.
The extent of those convective motions in the center of the star affect how much fuel the star can actually use when it's on the main sequence.
Yes.
Because the material from the edges of this zone, convection zone, can get mixed down to the center where it's being burned in the nuclear reactions in the star.
Sounds like overshoot.
Exactly. So different model makers use different amounts of convective overshoot.
Yes.
And that affects how much fuel the star has, and affects exactly at what point the star leaves the main sequence.
Correct.
Less overshoot means that the star has less fuel. It will leave earlier because it'll run out of fuel earlier.
Yes.
So this is actually a way of essentially calibrating that complicated process of convection. This is an observational showing of the consequences of this convection, something that's happening deep inside the star.
Okay.
So it's basically telling us it's giving the model maker something to think about if they pay attention, I suppose.
Pay attention, people. Yes. We are paying attention. At least I am.
So you have to, I mean, I think we've got a good case here. We've got masses for the stars, which is what the model makers want to have, you know, the initial conditions.
Right.
And we've got a whole bunch of different precisely measured characteristics for these stars that we can also give them to use on their models and see if they get the right answer. The physics and the observations are relatively simple and easy to understand. There can be a lot of analysis involved, I suppose, but
Sure.
we're confident of the characteristics of these stars. And knowing that these stars are in a very particular time of their life.
Yeah.
Not just it can be hard to tell for just random star that's out there in the galaxy, in the field of the galaxy, how exactly what phase of life it's in.
Right.
But in a star cluster like this, we get that extra information about exactly what stage of life the star is in. And all of that we present on a platter to the model makers.
That is awesome. Very awesome. Cool.
So it's kind of to sort of summarize this, this comes down at the end to allowing us to say something about the physics that's happening in the centers of these stars, the convection, but it also allows us to remove uncertainty about that particular bit of physics and select a group of models that seem to match all the observations that we have. If we believe that those models are representing reality, then we get an age for this cluster and a precise age. We say that it's 1.61 billion years plus or minus about 0.05. That's
pretty good. Yeah, it's pretty good. In fact, that was in the abstract. It was one of the things that caught my eye. It's, yeah, the precision of those masses and radii is impressive. Very impressive.
So, I mean, from an eclipsing binary person's point of view, that's about what you shoot for. Precisions that are better than 1% on masses and radii. If you really want to test our understanding of how the stars work. But you have to do that if you want to have the precision for the ages. Measuring the characteristics for a main sequence star that hasn't started to change its characteristics rapidly, that doesn't give you a good leverage on the age. But these stars that have started to leave and their characteristics are changing rapidly, those measurements do precisely give us the age.
Nice. Very good. And so it's from from those isochrones then that you extract the age?
Yeah.
Okay.
So primarily that little red ellipse up at the top right-hand corner.
Yes. Yes. Different ages, different isochrones, because different assumptions went into them. Yes.
So we basically rule out a couple of the isochrone sets because their physics doesn't seem to match the characteristics of the brighter star BD plus 37410A. They evolve off the main sequence before they get to that size. Almost 3 times the radius of the sun. Only the parsec and the OSDI IAC ones that are still in play, essentially.
All right. Yeah. All right. Good.
So, I mean, I guess that's kind of where I would leave the summary of the main points of the paper.
Cool.
Yeah.
Very good. Very good. Well, that was awesome. This is a nice BPAJ article. Very cool. Well, Eric, thank you so much for walking us through your very lovely BPAJ article. Appreciate it very much. Thank you. And you touched on it a little bit as you were walking through. So let me just push on it a little bit. You know, where do you think we go with this topic over, let's say, the next 2 to 5 years? Are there additional eclipsing binaries in this cluster? Are there other clusters where one could apply the analysis? It looks like there's some work to do on the theoretical models. So just sort of where do we go next steps, both observationally and I think theoretically on this topic.
Yeah, so I mean, in this particular cluster, I think there's maybe one or two eclipsing binaries that would be analyzable.
Okay.
That's not my main focus, really. I mean, I think this one star is probably the BD plus 37410 is probably the one that's going to give us the most interesting information for right now.
Okay.
What I've been focusing on, and I think is most interesting, is applying to the same thing to a bunch of other clusters. And there was a paper published by one of my students on the Praesepe star cluster, as one in the referee process on the Coma star cluster, both nearby groups of stars that are can give us some interesting information about stellar physics for stars of different mass. But sort of in general, I've been moving more in the direction of younger clusters to help us learn about more massive stars, especially trying to find an alternate way of finding the boundary between stars that supernova and don't.
Ooh, there's a topic.
Trying to figure out the masses of stars that produce the most massive white dwarfs.
Another way to phrase it? Yes, that's a very interesting question. Very cool, very cool. Well, I look forward to seeing those other articles come out and push forward this over the next couple of years. I think it'll be very interesting to see. So very nice. Cool. Well, Eric, thank you once again for walking us through your very lovely AJ article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thanks.
Thank you.